Welcome to the fascinating world of AI optimizers. I'm excited to take you on a journey through the algorithms that power machine learning. Think of optimizers as the GPS systems for artificial intelligence. They guide our models to find the best possible solutions in a vast landscape of possibilities. Today, we'll explore how these mathematical engines work, from the foundational SGD to the sophisticated atom optimizer. By the end of this video, you'll understand why choosing the right optimizer can make or break your AI project. So, what exactly are optimizers? Let's break this down into three key concepts. First, their goal. Optimizers exist to find the best parameters that minimize our loss function. Imagine you're trying to tune a guitar. You need to find exactly the right tension for each string. Second, navigation. They guide our model through an incredibly complex landscape of possibilities. We're talking about millions or even billions of parameters that need to be adjusted simultaneously. And third, efficiency. They need to reach the optimal solution as quickly and accurately as possible. Time is money in machine learning. Watch this demo ball. See how it's constantly moving, searching for the lowest point in our loss landscape? That's exactly what an optimizer does during training. Let's start with the granddaddy of all optimizers, stochastic gradient descent, or SGD. This is the foundation that everything else builds upon. SGD is beautifully simple. It takes steps proportional to the negative gradient. Think of it like this. Imagine you're blindfolded on a hillside and you want to reach the bottom. SGD would have you feel the slope with your feet and take a step in the steepest downward direction. Looking at our equation here, theta represents our perimeters. Eta is our learning rate, how big steps we take, and del J is the gradient, which direction is steepest. The animated graph shows SGD's path. Notice how it takes consistent, steady steps. It's reliable, but not always the fastest. SGD can get stuck in local minima and sometimes oscillates back and forth instead of making smooth progress. But here's the thing. SGD is still widely used because it's stable, predictable, and works well for many problems, especially when you have a lot of data. Now, what if we could give SGD a memory? That's exactly what momentum does. It's like adding inertia to our optimization process. Instead of just looking at the current gradient, momentum remembers previous directions and builds up velocity. It's like the difference between stopping and starting at every intersection versus maintaining speed on a highway. Look at our equation. We now have v for velocity, and beta, typically zero point 0.9, determines how much we remember from previous steps. See how the animation shows multiple lines? That's momentum accelerating through flat regions and smoothing out oscillations. The key advantage is that momentum helps us accelerate through consistent gradients, dampen oscillations in narrow valleys, and better escape shallow local minima. It's like our optimization ball has gained mass and can roll through small bumps instead of getting stuck. RMS prop introduces a game-changing concept, adaptive learning rates. Instead of using the same learning rate for all parameters, RMS prop adjusts the step size based on recent gradient history. Here's the brilliant insight. Some parameters might need big updates while others need tiny adjustments. RMS prop handles this automatically by maintaining a running average of squared gradients. Looking at our equation, E of g squared keeps track of how big our gradients have been recently. If gradients are consistently large, we reduce the learning rate. If they're small, we can be more aggressive. Notice our animation. See how it takes different size steps? Large steps initially, then smaller, more precise steps as it approaches the optimum. This makes RMS prop particularly good with sparse gradients like an NLP, non-stationary objectives, and problems where different parameters have different scales. It's like having a smart cruise control that adjusts speed based on road conditions. And now, ladies and gentlemen, meet Adam, the optimizer that changed everything. Adam combines the best of both worlds, Momentum's memory and RMS Prop's adaptive learning rates. Adam maintains two exponential moving averages, M for momentum, like a heavy ball rolling, and V for the adaptive learning rate, like smart brakes that adjust to conditions. The equations look complex, but the intuition is beautiful. Beta 1, usual 0.9, controls momentum. Beta 2, usually 0.999, controls the adaptive rate. And those M hat, V hat terms, those are bias corrections that prevent the optimizer from being too conservative at the start. Watch this multi-stage animation. See how Adam starts aggressively, then becomes more refined as it approaches the solution? That's the magic of combining momentum with adaptation. Adam has become the default choice for most deep learning practitioners because it works well out of the box, handles sparse gradients beautifully, requires minimal hyperparameter tuning, converges fast and reliably. It's like having a Formula One driver with perfect road sense. Now let's see them all in action. This visualization shows how different optimizers navigate the same loss landscape. The red ball represents SGD. Notice how it takes steady, consistent steps, but might be slower to reach the optimum. The green ball is SGD with momentum. See how it builds up speed and maintains direction? It's faster, but might overshoot. The blue ball is Adam. Look at that smooth, efficient path. It adapts its strategy as it goes, combining speed with precision. This isn't just academic. Choosing the right optimizer can mean the difference between a model that trains in hours versus days, or between achieving 85% accuracy on your task versus 95% accuracy. Let's wrap up with the key insights you need to remember. First, optimizers are absolutely crucial for effective neural network training. They're not just mathematical details, they're the engines that power AI. Second, Adam is often your best starting point. Unless you have a specific reason to use something else, Adam's combination of speed and reliability makes it the Swiss Army knife of optimizers. Third, understanding these fundamentals helps you make informed decisions. When Adam isn't working, you'll know whether to try SGD for stability or RMS prop for sparse data. Finally, don't be afraid to experiment. Different problems might need different approaches. Computer vision might love Adam, but some NLP tasks prefer AdaGrad, and reinforcement learning often sticks with SGD. The world of optimization is constantly evolving, with new algorithms like AdamW and LAMB pushing boundaries. But master these fundamentals, and you'll have the foundation to understand any optimizer that comes your way. Thanks for joining me on this optimization journey. If this helped you understand AI optimizers better, hit that like button and subscribe for more deep dives into machine learning concepts.